Now that you've had some time to practice writing orbital diagrams, full electron configurations, abbreviated electron configurations, and aware of the exceptions that occur in the periodic table, we're now going to take a look at how to draw one more expression of the electrons in the elements on our periodic table. In chemistry, the most important electrons are the valence electrons. You might remember from physical science that the valence electrons are the electrons that are involved in chemical reactions, and we can use our periodic table and the group an element is in to figure out how many valence electrons it has. You would have drawn these in Bohr diagrams. Well, we can also find these valence electrons by looking at the electron configuration. So first things first, our valence electrons will only ever be found in the outer energy level, highest level, S and P sublevels. So if you go back to page 77, you'll see that on my paper I have highlighted all of the highest energy level S and P electrons. So looking at the magnesium example, third energy level is higher than 2 and 1. So I highlighted the S electrons there. There are 2 electrons. So magnesium has 2 valence electrons. Phosphorus, highest energy level is 3. So there's 2 in the S, 3 in the P. Looking at vanadium, even though 3D fills last and 4S has jumped in line to get a couple of electrons, the 4th energy level is still higher than the 3rd. And so therefore those 2 valence electrons are the ones that are involved in chemical reactions, not the 3D3 electrons. Remember, 3rd energy level is lower than the 4th. So just because the 4th might fill up before the 3rd has even started, 4th is still higher and further out than the 3rd. Looking at germanium, 4th energy level is highest, so there's 2s and 2p electrons. That's a total of 4 valence electrons. In krypton, 4s and 4p, there's a total of 8 valence electrons. And with oxygen, 2s and 2p, so 2 electrons and 4, total of 6 valence electrons. So you can look at any electron configuration, find the highest energy level, count up the s's and p electrons that are there, and that tells you the valence electrons. What we're gradually going to work into is we're going to start showing you how elements will be coming together and either transferring their electrons, sharing their electrons in order to make chemical bonds. So we don't want to have to worry about drawing all of the electrons. Chapter 4 was based on us trying to find a map or an address for all of the electrons. We are interested now in moving into looking at just the valence electrons and showing you a different way to express them. It might look familiar from physical science, but we want it expressed in a really particular way. So when we're going to draw these Lewis diagrams, what we want to do is we want to treat the 4 sides of an element symbol as our S and P orbitals. So you might remember looking back at your Aufbau diagram and remember that any S you see has 1 box and any P that you see has 3, right? So 1 orbital and 3 orbitals. So we kind of want to follow that same system, and we want you to picture that if you were looking at any S and P for an element, we want our S electrons to appear on one side of our element symbol, and we want to show that we can follow Hund's rule and distribute the electrons that might end up in the P sublevel for that element by spreading them out. So I'll give you an example. If you were to look at aluminum, aluminum has an electron configuration right here that would be expressed as neon, 3s2, 3p1. So what we're going to do as a general rule, we're always going to place our s electrons only to the right-hand side. So since there are 2 s electrons, we're going to put those 2 electrons here. And since aluminum only has 1 electron in the P, we're going to place it around the bottom. If we were to go over to our next example and we were to look at a noble gas whose outer energy level is completely full, it's completely stable, it has that octet that all of the elements on the table are striving for, and we were to look at argon's configuration. So argon's configuration would be neon, 3s2, 3p6. So notice it has a total of 8 valence electrons. So my 2 s electrons would go here on the right-hand side. And what I would do is I'd start passing the electrons out. So first orbital, second, third. Now I can double up, fourth, fifth, and sixth. So electron 3, 4, 5, 6, 7, 8. And this is how I would draw a Lewis dot diagram. We want the s and the p electrons to go in a really specific place, okay? So the maximum you can ever have is 8 dots or 8 electrons, and they represent the octet. As far as helium goes, helium is, I don't want to say it's an exception, but keep in mind helium only has 2 electrons. It's part of group 18, but the reason why helium is placed in group 18 is because it only has, if you look at its orbital diagram, there's only one energy level that helium has, and that one energy level is completely full. So even though we often associate chemical stability with having 8 electrons, really what it is that your outermost energy level is full. And because helium only has one energy level and one sublevel, a 1s, it's completely full. That is why it is considered a noble gas. So let's take a look at some example elements. I'm gonna kind of verbally mention what their electron configuration is, and you can check that, you can look it up. So let's pick something from group 1. So group 1, let's say a lithium. We know that lithium would end 2s1. It doesn't have any p electrons. So because it's ending 2s1, I would write its chemical symbol, and I would put that 1 valence electron here to the right. If I were to pick something from group 2, like magnesium, magnesium is going to end 3s2. It doesn't have any p electrons in that energy level. So I would take magnesium's 2 valence electrons, and I would place them here. If I jump across the table, you saw the example I had for aluminum. Remember, aluminum, its configuration ends 3s2, 3p1. So if I have 2 electrons in the s and I have 1 electron in the p, that's where I place it. If I were to take a look at carbon, carbon is a great example of a group 14 element. So carbon is going to end 2s2, 2p2. So 2s2, 2p2. So I place one here and I place the second one there. Group 15 would use nitrogen. Let's use nitrogen as an example. Nitrogen is in group 15 and its configuration would end 2s2, 2p3. So here's my s2 and my p3, so p1, p2, p3. If I go next door and I take oxygen, we've done oxygen's configuration before. Okay, you can even see it on page 77. Notice it ended 2s2, 2p4. So I'm going to put these electrons on the right, and I'm going to pass those 4 electrons out. So here are my s2 electrons, and this is p1, p2, p3, p4. Picking something from group 17, an easy one to select would be fluorine. Fluorine is going to end 2s2, 2p5. There's my S2, and 1, 2, 3, 4, 5. So close to having an octet. That's why fluorine and the other halogens are very aggressive elements. And last, we have our group 18. I've already done argon, and they have that perfect configuration because their S is full and their P is full, and they are completely chemically stable. Now, what about the D block? The D block, we take a look at their configuration, and again, you look for the highest S and P electrons. So if I pull page 77 out, a great example of something from the D block would be vanadium. Vanadium, even though it filled up 3D last, notice 4s is the highest sublevel, it's the outermost sublevel. There's 2 electrons there. So anytime you're looking at something that's in the D block, you are always going to ignore those lower energy level D electrons because the highest energy level is always your S for those elements. So for vanadium, my highest electrons are here. One final thing I'll say is way back in physical science, you didn't look at electron configurations. You were using your periodic table, and you were told that the group was related to the valence electrons you have. So keep in mind, everybody in group 1 always has 1 valence electron. Every element in group 2 has 2 valence electrons. Here it can vary, but for the most part, all of the normal metals here, because they end something S2, then they would have 2 valence electrons. Are ones that are exceptions, like here and here, because they end something S1, they are going to have 1 valence electron. So chromium and molybdenum would have 1 valence electron. Copper, silver, and gold would have 1 valence electron because they would have, something S1. So, these guys, it's going to vary. When you get over to group 13, they have 3 valence electrons. 14 has 4, 15 has 5, 16 has 6, group 17 has 7, and group 18 has 8. And again, our only exception is helium. So I hope that helped and that makes some sense of how we're going to draw our Lewis dot diagrams that we'll eventually be using in showing chemical bonding.